And right now, the two kind of main focus areas in my lab are around thinking about social inequity and adaptive planning and how we can use systems modeling to advance progress in these areas with external partnerships. And so how I think about tackling social inequity is, again, I'm a systems modeler. And so I work with decision support models. And so I think about, how can we expand the capacity of our current decision support models that are traditionally used by planners to make water supply decisions to better capture and address the needs of under-resourced populations in particular. So one thing that we might kind of look at in a model is thinking about if we're concerned about drought resilience, for example, we have different options for how we might respond to a drought and a really wide range of different drought impacts that we're trying to capture. And so our models might help us look at some of these different options and how they might mitigate these different drought impacts. And as one example of how we can think about equity is in California, there's a lot of talk about desalination as a great climate-proof drought resilience option. And it has a lot of benefits, of course. It's a really reliable and clean source of water, but it also has major environmental impacts, and it's very, very expensive. And so if we think about expanding our definition of water security to include affordable water access for low-income populations, then it's possible that investing in desalination might actually harm water security by making water unaffordable for a larger fraction of the population. And the traditional urban water planning models that we have today don't have the capacity to assess these kinds of trade-offs. Awesome, thank you so much. So that's what we're working on there. And then the other big thing that we're working on in my group right now is adaptive planning. And so this kind of comes back to this idea of like these big infrastructure projects that we have traditionally relied on in the water sector, where we kind of have this predict and then act approach. So historically, we make our best predictions, maybe a couple scenarios for how much water supply we're going to need in the future. We add a big safety factor to address uncertainty, and that leads to these really large projects. And that's just getting worse as the climate is changing. So can we move to a more adaptive approach where rather than making predictions that we know for sure are going to be wrong, can we kind of monitor how the system is changing over time and adjust if and when necessary and develop infrastructure more nimbly and more modularly if and when we need it? So we're advancing the modeling capabilities to really understand under what circumstances this can actually be helpful as a strategy and what do we need to do in order to make it a more practical solution. So the talk today, I'm going to talk primarily about two projects, one kind of focused on the water affordability topic in Santa Cruz, and one on urban and modular water infrastructure planning in Santa Barbara, California. And I'll mention a little bit of the other adaptive planning work that we're doing as well. Okay, so diving into the first project, which is about climate and household water affordability in the city of Santa Cruz. And this is work that's being led by a number of current and former students in my lab. And the project is focused on Santa Cruz, California, which is just about an hour down the road from where I live in San Francisco. And Santa Cruz is an interesting place to study water affordability for a few reasons. The first is that it's really vulnerable to drought. So about 90% of its water comes from local surface water supplies. And so when there are droughts, it's really vulnerable to those impacts. And it's also a relatively wealthy city, but there's a huge amount of income inequality. So we have about 20% of the population living below the poverty line. So there are very significant water affordability challenges and a huge need for new infrastructure investments for climate resilience. And so we've been working with the city of Santa Cruz for the past several years now. And this is plots from all of the water billing data from the city going back to 2009. And so we had a really severe drought from about 2014 to 2017. And you can see that there were substantial conservation efforts that were made during the drought. And most of those have stayed afterwards. There's a little bit of rebound in water use. But if we look at monthly water bills, we can see that they really start to go up during the drought, and they've been just getting quite a lot higher. And a lot of this is driven by infrastructure reinvestment, which is continuing to go up. And so the median water bill in the city of Santa Cruz is about $150 a month right now, so quite high. So what we're doing is, again, thinking about how can we take the current decision support tools that planners are using to evaluate infrastructure and policy options and expand their capacity to be able to assess the impacts on household level water affordability. So this is a very simplified schematic of what a kind of traditional water supply systems model might look like, where we can look at different climate scenarios and see how they'll affect reliability at the system level. We can think about demand management and different infrastructure investments and assess how they will also affect system reliability as well as cost. So we don't currently have the capacity to assess affordability here. And so one of the things that we really need to add to this in order to be able to capture this is a better understanding of water demand patterns at the household level. So we've used this household level billing data in combination with sociodemographic and housing characteristics to be able to develop household level water demand estimates so that we can then get to household level water affordability by comparing people's water bills to their income. And then the other big piece of this that is really essential to understanding how household affordability might change in the future is infrastructure financing and rate design. And so we can think about infrastructure financing as what determines how costs are spread over time, and then rate design as really determining how those costs are spread out across different customers within the city. And so if we look now with different infrastructure options in the future, with different potential financing and rate structures, now we can really start to project, well, how might household affordability change for different groups of people within the city in the future. So the first project that I'll share with you in this area is led by my former postdoc, Ben. And we were just looking at kind of short-term drought impacts on household water affordability. And this is, again, during this recent drought that we had in Santa Cruz. And what we modeled here was assessing a handful of different infrastructure and drought response alternatives to the drought. So we had a few different drought scenarios. We looked at kind of the baseline drought that we had. We also looked at longer and more intense droughts. We then looked at different infrastructure options, so kind of sticking with what we have, or we could invest in some groundwater banking or a large-scale desalination plant. And then we also importantly looked at different short-term drought response options. So in particular, we looked at demand curtailment. And so this is what the city actually did during the drought, is they asked customers to cut back their water use by about 30%, which is about what actually happened. They also have the option to buy water on the market, so a supply side solution. And something that's really important is that when the utility does demand curtailment, they lose revenue and they have to recapture that revenue. And so they pass that on to customers through a drought surcharge. And so that leads people's water bills to go up with a fixed fee to offset the lost revenue from curtailment. So we looked at these different options in our model, and I'm showing you here the result from what happens if we address the drought through curtailment. And so you can see here we're really starting to draw down the water supply in our reservoir. This gap here is the 30% curtailment in demand that happens. And then in the bottom plot here, we're looking, well, what are the impacts of this on the utility costs at the bottom, and then water bills for low income and high income groups. And something interesting that we found here was that For the high income group in our model, water bills went down during the drought, but for the low income group, water bills went up during the drought. So this really highlights a substantial inequity in this particular response to the drought. And so why is that? It's because the drought had two different effects on water bills. So as I mentioned, there's this fixed surcharge that everyone's water bill goes up by about $20 a month. But then people's water bills are also going to down because they're using less water. So they have a lower volumetric charge on their water bill. And the high income households were using more water on average to begin with. So they have much more room to cut back. Whereas the low income households were really only using water for kind of basic purposes on average. And so they're not able to cut back as much. And that's why you have this difference in the net effect. So this was the kind of an example of how adding these new components to the model really allows us to assess the affordability and equity implications in different ways than we would have been able to capture previously. Yes?
So that was really interesting. Why did the utility cost go up during that period?
It wasn't that the costs went up, it's that the revenue went down because they were selling less water. Yeah.
Revenue loss.
Exactly. Exactly. Yeah. And as a public utility, they're required to pass that on. Yes.
Awesome. You're currently assessing affordability as the bill, and there's no objective way to assess affordability.
Yes.
Right?
Yes.
It's all subjective. But I'm curious about your choice because when you assess affordability in terms of the bill, that potentially includes obviously indoor use, but also outdoor use.
Mm-hmm.
And I'm just wondering if you have some thoughts about that. There's different implications for.
Yes. Yes, absolutely. There is. And we have, actually, I don't think I have it in this talk, but we have, we've done some work looking at a range of different affordability metrics and seeing how they compare. And in particular, looking at like delinquency, recurrent delinquency as a way to assess when people are like really truly having a hard time paying their water bills on a recurrent basis. So that's one avenue I think is promising that kind of addresses some of these issues. So it's absolutely true that this includes some outdoor water use, though I think for the low income populations in particular, there's a lot of multifamily housing in Santa Cruz, and most of the lower income census block groups are really predominantly multi-unit housing where there's not a lot of outdoor water use. So I would expect that most of the increase in water bills, or most of the water bills for lower income households is probably mostly indoor use.
Yeah, it's $20 flat fee.
Yeah, exactly. Exactly. Yeah. Yes.
Yeah. So I've thought about this exact issue in the past, and I wondered about a different solution.
Mm.
The problem the utility faces is that they will have a revenue, so they need to cover it. So they came up with this fixed charging fees. Right?
Yeah. Yeah.
However, if they had built that into the rate structure, anticipating that certain percentage of time they will have these kind of hits,
Yeah.
this would not be an issue, right? So it's really what you were saying earlier about the rate design, because if I was running the utility, I could go for a weather derivative or index insurance so that it smooths out the cost, and then I have the money when I need it. And then because it's smoothed out, I have it built into the regular rate structure and I don't do the spike. Is that?
Yeah. Yeah, and coming up, we'll look a little bit at rate design options. And Santa Cruz is starting to move in that direction. So part of why water bills have been going up over the past 7 years or so now is because they've added on an infrastructure reinvestment fee is what they call it, but it's really a way to kind of have reserves. But I think, one of the challenges is also that Santa Cruz has a rate design that has a really large fraction of their revenue recovery from volumetric charges. So they get about 80% of their revenue from volumetric charges. So it's a big buffer that they would have to to get. And they're doing that in part to promote conservation, and also to promote equity in the water bills, so that we don't have these large fixed fees. So I think there's a positive side to that, but then it makes it harder to do what you're talking about, to have this, because now you have a bigger revenue hit when more of your revenue is coming from volumetric.
The regulator and the regulator not a lot of flexibility, and how much is it because they haven't?
Yeah. Yeah, I think a lot of it is about the regulator. So let me move on, and we'll talk a little bit about that. Yes, so just to say, like, if we instead model buying on the supply side, where we don't have this surcharge, then you can see we don't have the same effect, and now everyone's water bills are going up because it's passed on through the volumetric charges instead of this drought surcharge. So yes, so coming back to Manu's point, then the rate design, we were looking at this result and thinking, well, yes, of course, the rate design is really what's driving this. And so what happens if we look at other rates? And so my former student, Adam, who's now working with Manu, led a paper looking at how different rate structures and surcharge structures really affect that impact of curtailment on affordability. And so one thing that's really important in California is that there is a lot of regulatory restriction on what municipal public water suppliers what kinds of rates they can charge. So we have a constitutional amendment called Proposition 218 that was passed a few decades ago now, that was a reform to tax law that says just that utilities can only charge customers for services that are provided to them. And it was intended as a way to prevent cities from trying to develop revenue for the general fund from their water bills and electric bills, which is good. But it's been interpreted very broadly in the court system to potentially mean that we can't even use volumetric rate structures in some cases. So there was one really notable court case that struck down an increasing block tier structure because it wasn't justified on the basis of actual services that were provided to customers. And so this has created a lot of legal risk and fear. So what Adam did is he looked at doing some legal analysis to assess what categories of rate structures are actually even viable in California under Prop 218. And so the ones that have this kind of hash marks are the ones that are legally not, we're going to say not commonly adopted because of the legal risk under Prop 218. And so we saw the biggest, this is looking at different base rate structures and optimizing those structures for cost. But then we had the biggest differences with the surcharge structure, which makes sense since the cost here is coming from that drought surcharge. And so you're seeing the low income water bills go up when we use this fixed drought surcharge, which is what we modeled previously. But we have a very, very low impact on the low-income households if we instead just use a volumetric-based surcharge instead of the fixed surcharge. So that I think would be another way to use rate design we could still have a drought surcharge, but if we could have it be volumetric instead of a flat fee, then it's substantially more equitable. Okay. So then the new direction that we're going in is, so far I've just been, these projects were just looking at short-term drought impacts on water affordability. But down the line, yeah, I think I probably just jiggled the mouse there a little bit. Thank you. Down the line, I would expect that long-term climate change impacts have a much larger effect on affordability through necessitating new infrastructure investments and the costs of those in the long term. And so that's the direction I'm going in my new career project, and this is led by my student Jenny. And so these are very preliminary results that I'm sure will change. So a big grain of salt here. But we have been looking at okay, Santa Cruz is expected to have less water supply in the future. And so what if we're just saying in this particular scenario, we use desalination to, we invest in desalination with as much capacity as we need in order to meet supply deficits in the future, and how might that affect water bills, and then the affordability ratio, which is the fraction of a person's income that they spend on their water bills. And we can look at this decades into the future, and we see that the distribution of household level water bills really goes up quite a lot. And that right now we have this is the kind of EPA recommendation for the affordability ratio should be less than 2%, and beyond that is when the EPA recommends we have an affordability challenge. And so right now we have about 30% of the population that is at that level, but we could even have the majority of the population start to exceed that ratio going forward. So we are looking here at different income classes. So this includes the median income at the block group level. Yes, so their recommendation is like looking at the whole city scale, so median income. So I think that's a big limitation, and we've done some other work that I don't have here on kind of the spatial aggregation bias that you get when you do that. So we've been trying to model this at the highest spatial resolution possible, and the income data that we have is median household income, and also the distribution of income within the block group level. And so we've been simulating households and individual households and their individual income using that block group level distribution. And then when we aggregate to income classes, we're getting a representation of the household level distribution within each individual income class. So it's not perfect, but we're trying to get at that to the best ability with the data that we have at the household level income, which is why this looks like a much worse picture than you would get if you use the median household income across the whole city. Yeah. Yes.
Does the median household income increase in the future, or is it at the current level?
That's a good question. We are currently assuming that it is constant at the current level, and we're doing all the analysis in 2020 dollars. But yes, it doesn't take into account economic growth, and I believe these results also are not yet taking into account demand changes in the future, but they in the latest version that Jenny is developing, we're accounting for demand. So I would expect these numbers to be not quite as large as they are now because of the demand reductions.
What triggered me was last week I attended a talk on energy with the same storyline. And the energy costs go way up. So if I start adding up the projected bills for each other things, you're soon over 100%.
Yeah, definitely. I know we've been trying to start to do some like combined water and energy affordability work because, right, I mean, and a lot of the climate factors you would expect to exacerbate both of those things at the same time. But I mean, yeah, I think that's the reality is a lot of these households will we'll get to that place if we don't have a kind of fundamentally new way of doing this. All right, so I don't know. Okay, there we go. Yeah, so kind of wrapping up from this particular project, right, we saw here that depending on the rate structures and the way in which we're handling drought response, the cost of drought resilience can disproportionately impact low-income households, and that rate design for affordable water access really needs to consider this hydrological variability in household level water use. So we can't just think about affordability programs separately from the water supply planning and the hydrology, and that climate change is really likely to have substantially larger impacts on water bills and affordability in the long term. So then I wanted to talk a little bit about equity in systems models more broadly. So this is one example that was really motivated by thinking about how can we make these models address equity issues more explicitly. So I've also been doing some work with folks across sustainability domains to think about what are some best practices in modeling more broadly. And so just to start off, I think it's important to kind of ground us in what we're talking about when we say equity. So I like these definitions where equality is a measure of differences across populations, and this is a purely descriptive measure. And so here we have this kind of simple example of people trying to watch the soccer game from behind a fence, and here we have an equal distribution of resources, so everyone has one box to stand on from behind this fence. Equity is different in that it is a measure of fairness that across different populations that considers context, and therefore it's inherently normative instead of just descriptive. And so as one example, in this particular context, we might see an unequal distribution of our resources, the box, as an equitable distribution because it allows everyone to have the same height to view the soccer game. And then when we think about justice, this would be the systems and structures that remove barriers to equity to begin with. So let's get rid of the fence that caused this whole problem to begin with. And then within equity, if we want to think about how to address this in decision support models, we need to be aware of the different dimensions of equity. So we have procedural equity, which is the ability for stakeholders to meaningfully participate in decision processes. And so in a modeling context, that might be, not just the planners and the decision makers, but having under-resourced and historically marginalized populations have a seat at the table as well. We can think about distributional equity as the distributions of those costs and benefits, so how we allocate those boxes. And then recognitional equity, which is respect for distinct identities, values, and knowledge systems. So recognizing that different groups of people might have different ideas of what's important when we consider equity. And importantly, we can think about these different components throughout the whole modeling process. So I was talking about we talked a little bit about metrics, but also kind of what modeling components and resolution we're looking at in our model, but all the way from the beginning to who's participating in the modeling process and what are the questions, all the way to assessing interventions. And so the project that I was talking to you about before is an example of looking at distributional equity, where we're focused really on selecting the modeling components and resolution as a way to assess equity. And when we're thinking about distributional equity, a framework that we like for how you can incorporate this into your model is to ask 3 questions. So first, what is being distributed, the unit, the scope, to who is it being distributed, and then the shape is the preferred shape of that distribution. And so in this context, a conceptual definition for equity that I like is, for water affordability in particular, is that we want to have water for drinking and sanitation without having to forgo other essential services due to the cost. And so then we can think about what we're distributing as the distribution of water costs. And our unit might be water bills. And then the scope is across income groups. And the shape, if we're following the EPA guidance, which is certainly not the only way to think about this, is that we don't want anyone above that 2% income threshold. So that's a way we can use this framework to do that. Another example that we have in the affordability space that really addresses the procedural component and is early in the modeling process to think about identifying who's at the table and what the purpose of the analysis is really about working directly with communities to inform local affordability efforts. And so this is a project that I did in collaboration with my colleague Khalid Osman, where we did an affordability assessment in the city of East Palo Alto, which is a low-income community right next to Stanford's campus. And we surveyed residents there about their water costs, and we collected their water bills, but we also found that there are substantial challenges with trust in drinking water quality there. And so people are buying a lot of bottled water and water filters as well. These are the different households that we surveyed and the costs of their water from different categories. And so we found that water bills are really making up only half of their water costs. And so if you're doing this traditional affordability assessment like the EPA recommends, just looking at the water bills versus the income without the community input on really what are their full costs of water and what is driving that, then you're really missing half of the affordability challenge in this particular population. And so that really gets back to your comment about how do we measure affordability. This would be really important to incorporate in this particular region.
That bottled water and well, maybe less so the bottled water, per unit is far more expensive than tap water.
Yeah.
Do you know if we'll substitute it for tap, like what the impacts would be?
If they substitute it for tap, like how much it more?
Bottled water.
Yes.
Right. They were just using.
Like how much lower the cost would be? That's a good question. We haven't done that analysis, but we should. Yeah, I would expect that it would be a lot lower. Though, yeah, absolutely, absolutely. Yeah, it's a huge problem here, and in this little city of East Palo Alto, there's 3 different water providers. Yeah, so the trust issues are really quite substantial. Yeah, but because of that, the water water costs are also really quite high because there's just not a lot of economies of scale that are being leveraged too. So I would expect it would go down a lot, but I mean you can see some of these water bills are still over $200 a month, and these are low-income households that are really, we did focus groups and they're really trying in a lot of ways to minimize their water use. Yeah. Yeah, so we have some recent papers that kind of look at again more frameworks how we can address this in systems models more broadly. Okay, so then for the rest of the talk, I wanted to kind of go back to the adaptive planning side of things, and we're looking at a case study in Santa Barbara, which is where this desalination plant that I was telling you about is. And this is work that was led by my former postdoc Marta, and co-advised with my colleague Megan Motter, who is a water treatment technology expert. And Santa Barbara is in Southern California, just north of LA. They get a lot of their water both from local service water supplies. They also get a lot of their water from Northern California imported through the State Water Project. And of course, they have this large seawater desalination plant as well, which was retrofitted many years later and is now operating and providing a lot of water supply to the city. And so they recently went through a water planning process called Water Vision Santa Barbara. And their primary concern is they are again worried about drought resilience, and they are again considering expanding their desalination capacity. But they really want to learn lessons from the past and not overdevelop these large infrastructure projects that aren't needed. So we've been working with them to think about, well, can we use adaptive planning as a way to assess the potential for small scale or modular water treatment technology as an alternative to these large scale investments. And so to assess that question of like how can we do adaptive urban water supply planning with decentralized water treatment technology, we developed this new modeling framework, which allows us to look at climate scenarios and water, the water resource system, but then also really couple that with a detailed model of the urban distribution system. So we can look at where we might site different decentralized water treatment projects throughout the city, and then couple that with a really detailed model, a process model of different treatment options and their different economic characteristics. And then for the adaptive planning strategy, what we do is we couple this simulation model with approaches from stochastic optimization that allows us to optimize these adaptive planning strategies. And what the adaptive planning strategy is it says under what hydrological conditions should we add new infrastructure, and what type of infrastructure. So here we're trying to actually monitor a drought as the drought unfolds over time, and only if and when we need it, add new capacity in response to that drought, instead of necessarily being prepared up front for the drought, and seeing under what kind of scenarios that approach is effective or ineffective. So let me walk you through how this works in more detail. So first, we develop climate scenarios looking at different kinds of droughts to do drought vulnerability assessment. So first, we have a scenario with kind of the historical characteristics of drought, and then we look at what if drought becomes more intense, longer, or more frequent. And then in each of these scenarios, we simulate thousands of different realizations for plausible droughts that might unfold in the future. So that's the climate side. Then we're looking at, again, a combination of centralized and decentralized water treatment technologies. So large scale seawater desalination, potable and non-potable reuse, and then also smaller scale decentralized potable and non-potable reuse, as well as curtailment. And importantly, these technologies have a lot of different characteristics, and certainly they have a really different levelized cost of water. So the more modular technologies have a higher cost of water at the unit scale. They're more expensive per gallon of water treated, but they also have different techno-economic characteristics. And one that is really important for us in adaptive planning is the time to deployment. So the modular technologies are more expensive, but because they're small and modular, they can come online more quickly, which turns out to be important when we're trying to take this adaptive approach. So we take the climate scenarios, we take the techno-economic characteristics, we put them in this model, and then we do this decision policy optimization as a way to develop these adaptive strategies. And the decision policies look like this. So they tell us, given some indicator of our system, once we exceed a certain threshold, then we take a set of actions. And the indicators that we're looking at is the SRI at different timescales. We're looking at water storage and changes in water storage. We're also looking at the amount of installed capacity and capacity that's under construction. The actions are those technology options that I showed on the previous slide at different sizes. And then what we do is we optimize these different tree structures so that we can test out lots and lots of different combinations of these policies and find a set of policies that allows us to maintain water reliability across all of these different drought scenarios with the lowest possible cost. So that's what we're optimizing for. So then let's look at some results. So first, we're looking at this across different drought characteristics as a way of understanding what characteristics of drought are really driving vulnerability in our system and under what conditions the adaptive approach is more effective. So when we look at long, mild droughts, we see in this case, we don't really need to add much more capacity at all. And that's because Santa Barbara has a relatively large amount of storage. So the storage that they have is really able to buffer most of these long, mild droughts. However, when we have short, intense droughts in the middle, we see that in red, this is the centralized capacity. And our model decides that we can't take this adaptive approach very much. We need to build a lot of decentralized capacity up front. And that's because the droughts happen so quickly and severely that the storage declines really rapidly, and we don't have enough time to bring on that decentralized capacity. But when we have frequent droughts that are not so long and also not so intense, this is when we're really able to take advantage of this decentralized approach. We build some centralized capacity up front, but we're really responding a lot with this decentralized capacity when the droughts unfold, and that substantially lowers the overall amount of capacity of infrastructure that we need. So here, now we're looking at, when we look at many, many different simulations of this, all of the kind of near Pareto optimal solutions, and we can look at this across the historical drought, the different drought characteristics, and then we of course want to be robust to all the droughts. So what happens if we want to be robust across all the droughts? And we can see that it's really when we have the intense droughts that we add a lot of capacity, and we really add a similar amount of capacity to be prepared for all of those droughts as we do for just the short and intense ones. And we can also look at what fraction of that capacity is decentralized in the different scenarios. And interestingly, we see that when we're being prepared for all of the droughts, we have a pretty substantial fraction, close to 20% of that capacity is decentralized. So even though it's not effective for managing all the different drought types, it's an important part of the portfolio. Yeah, sure.
You're talking about infrastructure capacity?
Yes.
So, does that assume that in the drought, the water is there to fill the capacity? I'm kind of a little about your distinction between water itself that fills the infrastructure capacity. Or
yes. This is infrastructure capacity, and so the desalination is modeled as, you know, totally rainfall independent, and we can have it when we need it. But the centralized and decentralized reuse do consider the fact that we have to have the water available from the water system in order to implement. Yeah, so it's all those things together. Yes, very good question. Thank you for clarifying that. Okay. Another thing that we can look at is analyzing these adaptive policies and trying to assess, well, what piece of information was used to trigger the new infrastructure investment. And so when we have these historical droughts, it's really the SRI that is driving the investment. Whereas when we have long and mild droughts, what we're doing is we're monitoring storage levels. And then when storage gets too low, we trigger new investments. With the short intense droughts, it's the technology. So it's just how much capacity do we have? And if we don't have enough capacity, we need to add more. With being robust to all of the droughts simultaneously, interestingly, it looks pretty similar to the short intense droughts. But we do have a little bit more responding to shortage over time. And so then this also drives the total cost of being prepared for these different categories of droughts, where again you can see that being prepared for the short intense droughts is really about the same cost as being prepared for all of them. So it's really that drought intensity that is driving vulnerability and driving cost in the city. Yes.
Just a small detailed question. How did you clarify the same question?
Oh, thank you.
What's the economy of scale going from decentralized to centralized reuse that was considered here? Because if you include conveyance in that, in the work we have done, the answer changes dramatically.
Yeah.
And so I'm curious how that was.
Yeah, I don't have those cost curves offhand, but we do include the decentralized capacity is like cited at different points in the distribution system. So we're not adding additional conveyance. We're kind of assuming that there's a place in the distribution network already where we can add them. And then we're considering the topology of the distribution network and the energy cost associated with siting these in different locations. But it is true that there, you know, realistically would be additional yeah.
You were planning to build a conveyor system for reuse. You avoid that.
Yeah.
So your actual marginal cost for decentralized plus lack of conveyance to move the stuff
right.
back
Right.
is favorable relative to a centralized system for reuse where you're moving water both ways.
Right, that makes sense. That makes sense. But here in both cases, we're assuming that we're using the existing infrastructure network. Yeah. Yeah.
Work was not looking at the intermittent sort.
Yeah.
If I'm doing the wastewater reuse system, we were finding that the decentralized reuse is inevitably cheaper than centralized reuse. You would consider that even in a waste strategy.
Oh, interesting. Because of the conveyance costs of the, yeah,
Conveyance is
yeah,
70 to 80% of the cost. So,
Yeah.
you know, it's worth taking that.
yeah. Yeah, I guess it depends on where you are and what's already going on. In this case, the seawater desalination, they're considering an expansion of their existing plant, so you don't need a lot of new conveyance there. Yeah,
No, no,
Yeah.
so the
Or maybe I'm not
wastewater
following.
reuse, there was a centralized system and a decentralized.
Yeah, yeah.
That's the only two that I'm comparing.
Oh, I see, I
The
see, I see.
centralized wastewater reuse
I
would
see.
go away.
Yeah.
To consider the conveyance cost of bringing the water back.
Yeah, yeah. Yeah, that's a good question.
If you
We
don't
should look
do
at that.
reuse,
Yeah,
then it doesn't.
yeah,
But the minute you consider reuse, then a network hybrid structure, which is highly distributed,
yeah,
typically is cheaper than, you know, especially where topography is a factor, which is here.
yeah,
It's typically cheaper than having another pump pipe system bringing it all the way back.
yeah, absolutely.
If you know, and since that gives you the ability to deal with a certain type of drought, that would be interesting.
Mhm.
Because, if it screens out the centralized reuse altogether,
Mhm.
then strategically you can optimize much better.
Yeah, that makes a lot of sense. That makes a lot of sense. Yeah, that would be really interesting to include that part in the analysis here. It might look substantially better. Yeah.
Is the water control part is the water utilities or is it a separate entity?
Here we're
So is-
no, it's controlled by the city. Yeah,
It is.
so it's combined. Yeah, good questions. Okay, so that was kind of the starting point in this analysis in Santa Barbara. We also then wanted to look at, well, we assumed that the technology costs and the kind of governance structure that we have today exists in all of our cost estimates. But then we wanted to look at, well, what different types of innovations might really further drive the effectiveness of the modular technologies and the adaptive approach. And we're specifically thinking about, are there specific technology innovations that would really lend themselves to this approach in particular, and also policy innovations. And so what we're thinking about here is trying to assess technology innovations, which is typically done at the unit scale. And so going from this kind of unit scale technology cost to what is the impact of those technology or policy innovations at the system level in our ability to meet water reliability across the whole system. And so we're hypothesizing that there might be a nonlinear relationship between the unit level innovation benefit and the system level impact. And we're hoping that by kind of analyzing this innovation space at the system level, that we'll then be able to kind of identify system vulnerabilities that might come up when we're changing different technologies, and also set innovation targets that would specifically help. So one result here that we're looking at is the same modeling analysis that we did before, but now we're doing some sensitivity analysis to look at different types of innovation. So kind of our base case is here in the middle, and then we're looking at the vertical axis at innovations that change the CapEx ratio. So if we can lower the CapEx ratio, then we are reducing the capital costs of new technologies, and now of spend and operating costs. And then on the horizontal axis, we're looking at the deployment time. So once we make a decision that now we're going to develop new infrastructure, how long does it actually take before that technology can come online? And so if we look at the top here, we see that if we have really capital intensive infrastructure, then the deployment time doesn't really have much of effect. There's really no point in kind of streamlining your permitting process, being able to deploy these more quickly if you have these really capital intensive technologies. But where we're really able to capture quite a lot of cost decrease is when we can have low CapEx technologies coupled with really short deployment times. And this is when we have that sweet spot where we're really able to rely almost entirely now on the modular adaptive approach. But if things were to get worse, and now the deployment time becomes a lot longer, then this gets worse. And now there's really really no incentive in our current modeling approach to pair or to really rely on these modular technologies. So right now, California is considering new permitting and regulation around seawater desalination in particular. So we use this analysis to submit a public comment showing the benefits of really being able to expedite the permitting process and pre-permit some of these projects as a way to have reliability during these droughts with less infrastructure. So looking across this project, we saw that, that climate matters a lot. So the drought intensity really drives vulnerability and cost in Santa Barbara. This has important policy implications in California in particular, because right now the state requires municipalities to develop their drought contingency plans based on a design drought that is defined by duration. So we're required to just plan for a 5-year drought. So this suggests we should really be thinking about drought intensity when we're developing these drought contingency plans as well. The scale really matters a lot. So being able to connect the process level modeling and the distribution network all the way back to the climate is what really allowed us to get at the benefit of this approach. And then the characteristics of the technology matter quite a lot as well. And again, kind of looking across these case studies, the way I'm thinking about them together is that we want to have water supply in our cities that is both reliable and affordable. And so we're trying to advance that both by reducing the cost of reliability through adaptive planning, and then making sure that when we do have these increased costs, that we have policy solutions that can pass those on in more equitable ways. I also wanted to just really briefly, I'll wrap up soon here, really briefly mention some of the other adaptive planning projects that we have as well. So we have one project in the Maipo Basin in Chile, which supplies water to the city of Santiago. What's interesting here is that this is a glacier-dominated basin. And so right now, glacier melt during the summertime is really buffering the substantial drought conditions that they're having. They're in the middle of a 13-year drought right now. But as the climate is changing, there's a lot of uncertainty about how quickly the glaciers will recede. And by the end of the century, we might have no glacier melt at all, or we might have increased glacier melt versus today. But Chile currently has specific drought indicators that are codified into their federal legislation, and they're looking to update and reform their water code. So we're looking at how often do you need to adapt these drought indicators over time, and what components of the hydrological cycle would you want to use as your drought monitoring strategy as the climate changes, especially since there is so much uncertainty. So we're able to use a kind of similar optimization approach to really assess how do we adapt the indicators in addition to just the actions that we're using to climate change. Then we're also doing some kind of basin scale work looking at the impact of climate oscillations on adaptive planning. So I have just 2 slides on this. So here I'm kind of stepping back to try to ask a question about how do contrasting climate oscillation patterns affect adaptive planning more generally. So we kind of have a more generic model of a water supply system. We're looking at different climate oscillations across sub-Saharan Africa, and then we see how they affect our ability to do adaptive planning. And one interesting result that came out of this is here we're looking, these different colors are climate oscillations with different lengths. So the longer oscillations on the top have a period of about 10 to 30 years. And the shorter ones are more from like the ENSO cycle, so on the order of 3 to 5 years. And we know in general that the cost of managing low frequency climate variability is really expensive, right? This is when we need really large storage projects. But if we are able to do interventions that respond to climate oscillations by monitoring things like the ENSO index, and we also have the institutional capacity to revisit decisions very frequently, then we're able to really reduce the cost of managing these large-scale climate oscillations, the long oscillations, really substantially. So another example of how climate plays a role in how effective adaptive planning is as a strategy. And then finally, just wanted to mention, I've been talking a lot about climate today, but of course there's a huge amount of uncertainty in demand patterns, especially in cities with urbanization. And this is a plot from, I think, the city of San Diego, but I won't pick on them because there are many, many examples of plots like this where we have the actual demand and demand projections that are really overestimating demand year after year after year. So we are looking to develop uncertainty characterizations of demand in these cities in the future, and then also include that in our adaptive planning processes. And in general, the main goal for me is to be able to advance this as a practical solution for climate resilience. And so looking across the work that we've done in this area so far, there's a number of things about the climate infrastructure system and also the governance that is really important for determining under what conditions this can actually be useful. So we found that low frequency climate variability makes it effective. It's also helpful when near-term indicators are predictive of long-term trends and when we have the opportunity to reduce uncertainty in the future. Thinking about the infrastructure system, it's helpful when we have a lot of storage that can buffer climate variability, and that allows us to kind of effectively lengthen the time scale of variability. It's helpful when capital costs are low and economies of scale are small. And then from a governance perspective, it's helpful when new infrastructure can be developed quickly and when planners can revisit decisions often. And so then thinking about, well, what if this is what really drives the effectiveness of it, what kinds of innovations would we need in order to enhance the effectiveness? We can think about improved climate predictions on the timescale relevant to interventions. New forms of water storage, like managed aquifer recharge, could be really helpful. Modular water treatment technology. And then things on the governance side, like institutional flexibility and the ability to pre-permit infrastructure projects to reduce that time to deployment. So I will stop there, and I want to thank my lab for all of their hard work and also the funders of this work. Thank you.